Welcome back to this lecture on nested quantifiers. In this segment, we're going to discuss the concept of a logical consequence. So here is the definition of logical consequence, which we denote with this symbol here, which means that T is a logical consequence of S, which by definition means whenever S is true, then T must be true. That's what logical consequence means. That's just a definition. Now, be aware that this symbol is not a logical connective. In other words, this expression here is not a compound proposition of predicate logic. It's not a part of logic at all. This is just an abbreviated way of writing down the fact that T follows or logically follows from S, which, by the way, is another way of saying that T is a logical consequence of S. Now let's consider our first two propositions and the claim that one, namely this one, is a logical consequence of this one. Actually, that's a question I'm asking you. So what you have to answer is it true that whenever this proposition is true, then this proposition must also be true? Now, the way to prove this, if it's the case, is to argue for every possible domain of X and every possible domain of Y and every possible relationship denoted by P. That's a pretty tough thing to do. Now, in this case, it turns out this logical consequence is not true. So that's a little bit easier to prove since all you have to do is come up with a counterexample. So let's pick a particular universe U. Let's pick the simplest possible one. Let's say one with two elements. Now, how are we going to represent the predicate P? Notice this is a binary predicate. So we can't use the usual representation of predicates as circles or sets. Remember, this used to work because when you have a predicate, a unary predicate like d of x, x is a dog, say, well, every element in the universe either has the property or it doesn't. So you can distinguish those elements that do by circling them or putting them together in a set. And that distinguishes them from every other element in the set that doesn't have the property. Now we can't do that here because the predicate is a binary predicate. So it's not a property of a single element. It's a relationship between two elements. So we need to find a way to represent pictorially the relationship between two elements. And an easy way to do that in this representation here is to draw an arrow from one element to another if the property P holds between those two elements. So this black arrow here going from the element called A to the element called B simply represent the fact that the proposition P of AB is true. So in this pictorial representation, every arrow represents a single proposition. Let's say I wanted to add another proposition, say P of B and B. How would I represent that graphically? Well, P of BB means that B is in a relationship with itself, which means I must draw an arrow from B to itself. And that represents the proposition P of BB. Notice how the arrows have a direction. So if I wanted to represent the fact that B is in relationship to A, or PBA, I would have to draw an arrow from B to A. But let's say I don't do that and I stop right there. This is the example I want to consider right now. Now, under this example, what is the truth value of this proposition? Is it true that for every element X in the universe, there is an arrow from X to some other element in the universe? And the answer is yes, because if you look at A, it has at least one arrow going out of it. And if you look at B, it has at least one arrow going out of it. And these are the only two elements in the universe. Therefore, this leftmost proposition is true under this interpretation or this example. Now, how about the second proposition? It says there exists an X So there exists one element in the universe for which P of xy is true for every element in the universe. So graphically that means, is there an element here in this universe that has arrows connecting it to every element in the universe? And the answer is no, because A has an arrow to B but not to itself, so it's not connected to every element in the universe. And B has an arrow to itself but not to A. So B is not connected to all the elements in the universe. And these are the only two elements, so therefore there's no such element, which is what this states. And therefore this rightmost proposition is false. And as a result, we find a situation where this proposition is true while this one is false. Therefore, the logical consequence that was asked about does not hold. Now let's consider a second example, namely, is it true that if there exists x for all y, P of xy is true, then for all x there exists y, P of xy must also be true? Please stop the video and figure out the answer for yourself. So, turns out this is not a valid logical consequence. So that's pretty easy to prove using a counterexample. This time I'm going to use a domain with 3 elements. And notice this element here is connected to every other element in the universe, including itself. So it has 3 arrows going out of it because the universe contains 3 elements. In particular, what this means is there is an element x that is connected to every other or to every element in the universe, making this proposition true. That's what this proposition states. Now, let's check the truth value of this proposition under this example. What it says is, for every element in the universe, it must have an arrow going out of it connecting it to some element y. Well, that's not true because, for example, this element right here does not have an arrow going out of it. By the way, neither does this one, but only one of them suffices to argue that this proposition is false under this example. And therefore, this example is a counterexample for the logical consequence, since we proved that there exists a situation where the first proposition is true and the second one is false. And that concludes this example. Now let's turn to our third example, namely this logical equivalence. Where does it hold? Again, I'll let you think about this on your own, and I'll talk to you in a few minutes. Okay, so this one is different. It turns out this logical equivalence actually holds. Now, to prove this, we can't use a diagram because we wouldn't be covering every possible interpretation and every possible domain for x and y. So here we have to reason in the abstract. And here is one way to do it. We're going to argue that whenever this is true, this one must also be true. So all we do is assume that this proposition is true. See what happens. This proposition states that, remember, when P of xy holds, that means there must be an arrow from x to y in our little diagrams. So if there exists a y such that P of xy holds for every x, that means there must be at least one element in the universe that has arrows coming into it from every element in the universe, including itself. So if that is the case, then I will argue that this must also be true. What this is saying is that for every element in the universe, x, it must point to something. Call it y. Well, that must be the case because we assume that there is one element in the universe here that has arrows pointing to it from every single element in the universe. Therefore, for every single element, there is indeed an element that they point to. That's the one we chose over here. So in conclusion, if the first proposition is true, then the second must be true. And this is indeed a logical consequence. So let me call these two propositions S and T respectively. So we just proved that T is a logical consequence of S. Now I want you to pause the video and figure out whether S is also a logical consequence of T. You got it? Okay, the answer is no. S does not logically follow from T. A simple counterexample will prove that. Let's say a universe with 3 elements, where every element has at least one arrow going out of it, thereby making T true. But is S true or false in this case? Well, we can see on the diagram that there are no elements here with arrows going into it from every element in the universe. Therefore, S is false, but T was true, so T or S is not a logical consequence of T. And what that means in particular is that S and T are not logically equivalent. I'm trying to connect what you already know here to the new concept of logical consequence. In particular, what does it mean for two propositions to be logically equivalent? That means they are true at the same time and false at the same time. In case you didn't realize it, if S is logically equivalent to T, then it must be the case that T is a logical consequence of S, and also S is a logical consequence of T. Having the logical consequence in both directions is the same thing as being logically equivalent. In this case, there's no logical equivalence because the logical consequence does not work in this direction. Let us conclude this segment with the fourth and last example. I'm going to ask you again to pause the video and to answer this question on your own, namely, does this proposition logically follow from this one? Now, it turns out the answer is no. This is not a logical consequence, and I'll let you prove that if you haven't done it yet using a counterexample.